Java has 6 numeric types for integers and floating point numbers that can be used with the operators plus for addition, minus for subtraction, asterisk for multiplication, the / for integer division, and the percent sign or remainder operator for modulus arithmetic. Each data type is allotted a specific amount of memory for a variable that is declared to have that data type. Looking at the table on this slide, you will see that a variable of type int is allowed 32 bits or 4 bytes, and a double is allocated 64 bits or 8 bytes. The amount of storage allocated determines the range of values that a variable of that data type can hold. The 6 data types shown in the table are numeric data types, that is, they hold a numeric value. Of these data types, 4 types, byte, short, int, and long, hold integer data, that is, numbers without a decimal point. 2 data types, float and double, hold real number data or floating point data, that is, numbers with a decimal point or a fractional component. In our class, we will use for the most part the int for integer types and double for real numbers or floating point numbers. These 6 data types are primitive data types in Java. Later, we will also introduce the remaining 2 primitive data types, Boolean and char. Recall our discussion on obtaining user input. We said that we must use the scanner class to do so, and we import the scanner class, create a scanner object, and use that scanner object to read in values from the user. Before we can read in information from the user, we must prompt the user for the information using a print statement, and it is at this point that we're now ready to receive the user's input. When we receive the user's input, we usually need to store that input somewhere so we can access it later in the program. And usually we store it in a variable, although it is possible that it could be stored in a constant. The data type of the variable or the constant into which this information is stored determines the method that we use to obtain the data from the user. If we are reading in an integer and storing it in a variable of the type int, we will need to use the method nextInt, as shown in the table. If we're using a real number and storing it in a variable of type double, then we would use the method nextDouble, as shown in the table. When we use the scanner to read in the data, we must call the scanner by name and use the dot notation to call the appropriate method. So if we want to read in an integer a variable of type int using the scanner created on this slide, we use integer, the name of the scanner, followed by a period, which we read as dot, followed by nextInt, and ending in a semicolon. The operators for numeric data types include the standard arithmetic operators: addition, subtraction, multiplication, denoted by an asterisk, division, denoted by a /, and remainder or modulus, denoted by the percent sign. When we use the division operator, the result will be an integer unless one of the operands is a real number, that is, of type float or double. It's very important to remember that when both operands are an integer value, the result of the division is an integer. That is, the quotient is an integer. And that integer will have been truncated. That is, we completely ignore the fractional part. So the integer 5 divided by the integer 2 yields the integer value 2, not 2.5 and not 3, as you might expect. In order to retain the information following the decimal point, one of the operands must be of type double, of type float, or a real literal. So for instance, 5.0 divided by 2 will yield a double value 2.5. The integer 5 divided by the real number 2.0 will yield the value 2.5, and 5.0 divided by 2.0 likewise will yield a double value 2.5. When we perform modulus arithmetic using the remainder operator, that is the percent sign, the result will always be an integer, that is the remainder after division. So 5 modulo 2 is equal to 1, because the remainder when we divide 5 by 2 is 1. However, 2 modulo 5 is equal to 2, because the remainder when we divide 2 by 5 is 2. And likewise, 5 modulo 5 is equal to 0. It's important to understand that when we use the remainder operator, the result will always be an integer number in the range 0 to 1 less than the divisor, that is the value following the percent sign. Additionally, the result will only be negative if the dividend, that is the number in front of the percent sign, is negative. So negative 5 modulo 2 is equal to negative 1. The remainder operator is very useful in programming. Let us consider a few applications. If we want to determine if an integer value that is stored in a variable called number is even or odd, we can do so by applying the remainder operator and observing the result. Number mod 2 equal to 0 means that number is even, otherwise number is odd. Another way to say this is that if number mod 2 is equal to 1, then number is odd, otherwise it would be even. Recall that the result of using the remainder operator with a divisor of 2 can only be 0 or 1. Let's consider another example. Suppose that today is Saturday and you and your friends are going to meet up in 10 days. What day of the week is in 10 days? Well, since there's 7 days in a week, we will use modulo 7. Therefore, the result will be an integer from 0 to 6, exactly 7 values, and each of these values will represent a specific day of the week. We will denote 0 to represent Sunday, 1 to represent Monday, and so on. The expression that we use to make this determination is 6, the value of the current day of the week, Saturday, plus 10, because we are considering what day it will be in 10 days, modulo 7, which yields a result of 2, and 2 corresponds to Tuesday. Therefore, in 10 days, we will meet our friends on a Tuesday. It is very important to understand that any calculations involving floating point numbers, that is, float or double data types, are approximations. Floating point numbers are not stored with complete accuracy because they are allotted a finite amount of space and must round off the portion after the decimal point. Integers, however, yield a precise integer result. In Java, we are given a method that allows us to easily use exponents in our computations. The method is named math.pal. To use math.pal, we must be sure to capitalize the M in math and include 2 numbers or parameters inside the parenthesis. The first number is the base, followed by a comma, and the second number is the exponent. There are no spaces between the word math, the decimal point, the word pal, and the opening parentheses. We generally include a space after the comma between the parameters in the parentheses, just for clarity. Although the 2 numbers in the parentheses, again, we're calling them parameters, can be positive or negative, integer or floating point. You will recall from algebra that if we want to compute the square root of a number, that is equivalent to raising a number to the 1/2, or the 0.5 power, we simply use 0.5 as the second parameter representing the exponent. If you're not familiar with the rules of exponents, it will be necessary for you to review them on your own at this point. A literal is a value that appears in the program and does not require computation. It literally or explicitly states the value without the need for further evaluation. So any numbers such as 9, -44, 33.7 are all literal values. However, 8 plus 1 is not a literal value because it requires computation to obtain the result 9. We can assign literal values to an integer variable as long as the value is within the allowable range of the data type. Recall from our previous slide that the range of variables of type int is between -2 to the 31st power and 2 to the 31st power minus 1. Likewise, floating point literals default to the double data type. So 5.0 would be considered a double type, not a float type. If we want to assure that it is stored as a float, we have to append the uppercase or lowercase f at the end of the literal. Likewise, if we want to assure that a number will be stored as a double, we can append the letter D, lowercase or uppercase, at the end of the literal. Because the data type double allots greater storage space in memory, values of type double are more accurate than those of type float. And it's for this reason that in this class we will use double for all real numbers except the rarest occasion. We can specify floating point literals in scientific notation using the lowercase or uppercase e to denote the appropriate power of 10. Thus the number 123.456 in scientific notation is 1.23456 e plus 2, where the plus sign is optional. And the number 0.012346 in scientific notation is represented as 1.23456 e negative 2, where the negative sign is required.